Well, good morning, everybody. Welcome to Code Camp. Yeah, let's hear it for Code Camp. So I've been coming to Code Camp every year since it started, and I love Code Camp. And I want to thank PayPal for letting us use their campus today. So I've got something to talk about, how JavaScript works. So some of you might remember 10 years ago, I wrote a book called JavaScript, The Good Parts. Anybody heard of it? A couple of hands go up. Yeah. So it did, hello? Oh, so now you recognize it, right? So anybody seen this book? Yeah. A few more hands went up. So it's been 10 years since that book came out, and I look at the possibility of doing a revision of it because, you know, most software books are obsolete before they're printed, and this one had gone 10 years, so maybe there was something new to put in it. So in negotiating with O'Reilly, it turned out that I don't own the copyright on this book, and O'Reilly doesn't own the copyright on this book. Yahoo owns the copyright on this book. When I was at Yahoo, I started the Yahoo Press because I wanted to be able to write books on company time. And I didn't realize that having done that, I'd given up the copyright on this, so I can't revise it. Because I don't know anybody at Yahoo anymore. I don't even know what Yahoo is anymore. So I thought, well, do I want to write a new book? And the big question there was, is there any more to say? Because we've been doing this stuff for another decade, and there have been lots and lots of other good books finally coming out about JavaScript. And is there anything that I can say that's substantial and important that hasn't been already said? And in thinking deeply about it, I think there is. And so this is the message that's going to be in the new book, that JavaScript is the transitional language to the next paradigm. JavaScript is sort of unique in that it was not designed as a general computation language. It was designed as a language for doing user interfaces in real time, highly interactive programs, which is a very different model. It's a general language, so it can do everything that the other languages can do. And the other languages can do what JavaScript does, but JavaScript was created with this particular focus. And yeah. You can't hear me in the back? Okay. Is this better? Can you hear me now? Can anybody hear me? Okay. We're getting some feedback now. Okay, so he's going to write it? Sorry. Okay, so JavaScript sort of helps us to approach the next paradigm in programming, which I think is going to be globally distributed, secure, eventual programming. All computing up until this point has been sequential programming, all happening within one box. If you look at the work of Church's lambda calculus and you look at the work of Turing's universal Turing machine, those are the models of computation that we're using in all of computer science. But those machines were constrained to doing computation within one box. And that's not the way the world works anymore. We've got the internet now, and everything is distributed all over the place. And so the old model doesn't work. There's no way in the lambda calculus to describe data that exists on one machine and not on another. And that turns out to be a really important thing in the way we work. So we're going to have to go to a new paradigm. And I think that paradigm obviously is globally distributed, secure, eventual programming. And JavaScript was actually created to do that. Its first job was interacting with humans, interacting with another machine on the other side of the network. So there's a lot that JavaScript got right, and so I think that can help us to go forward. So that inspired this book. That's why I think there is something more to say. The reason why it isn't clear how we get to the next paradigm is because there's a danger that all aging programming languages face, and it's like a bad plastic surgery addiction, that they're constantly trying to glue new features in order to remain Beautiful? Well, that doesn't work. To be young looking or hip or attractive, because they're afraid that the kids will abandon them if they're not keeping up with all the latest features. And so the language, this happens not just to JavaScript, but all of the aging languages are experiencing this, that their standards committees are kind of getting out of control and putting a lot of junk into the languages. And most of that junk is not propelling us toward the next paradigm. They're actually keeping us cemented in the old paradigm. So this is the cover of the book. The shocking blockbuster that dares to rip the lid off of behind the scenes, how JavaScript works. And it is not for sale. I was really hoping to have copies of it here for you today. Unfortunately, it got held up in the printer. It turns out books are not made out of lead anymore. They're made out of bits. And things go wrong with bits. And so I submitted it to the printer, and they say, we can't print this file, and they can't tell me why. And we've been going around that. So I'm confident that eventually we will get this done, and the book will get printed, hopefully next week. But, it's hopefully this week. So it's software, right? So it'll get done when it gets done. Books are software now. Everything is software now. And that's good, and it's also bad, because we're not very good at software yet. So if you want to know what the book is about, this is the executive one-sentence summary. Compared to a decade ago, I think less of the language is good, but I think that good part is better. So when I started writing the book, I began by creating a tool, a manuscript tool. So I would write the book in this manuscript language, and it would be written in JavaScript, and then it would translate it into HTML, and then that would get translated into PDF. And I was having a really good time writing that tool. And eventually I noticed that I wasn't making any progress on the book. I was just having so much fun working on this tool that I had budgeted 1 month to do all the writing. And after that month, I thought, well, I'm about halfway through. And a month later, I thought, well, I'm about halfway through. And the next month, I thought, well, I'm about halfway through. It turned into a software project. And so I thought, okay, I have to stop working on this tool, because as fun as it is, it's really distracting, and I'm not writing. And so I took all of the stuff that I had written to that point, converted it into HTML, and then I thought, I'll just finish the book in HTML. But I had another year of writing left after that. And so writing a book in HTML is incredibly painful. There's a reason why GitHub and Wikipedia have Markdown languages. If those systems depended on HTML for their contributions, they would not exist. That it's just, I don't know how this became the world standard, but it's really awful. It's painful, it's ugly, it's fragile, it's nasty. So if you're reading the book and you're wondering, why is this guy so pissed off all the time? Because of that. If I could have done it, or I could do it over again, but I'm not going to do it over again. But if I were doing it over again, I would use Knuth's literate programming tools. When I started, I did not know how much program was going to be in the book. And his tools are extremely good at representing programs. And I think it turned out okay anyway, but his tools would have been much easier to use than writing it directly in HTML. So in preparing the book, I spent a lot of time thinking deeply about all of the assumptions that we have in the way we do our work. That there's a tendency to accept the way things are and assume that things are the way they are because that's the best possible way of doing it. And often that's not true. And the only way you can figure that out is to question all of the assumptions. And I looked at really fundamental things like, is the origin 0 or 1? When we started programming, the first programming languages had an origin of 1. Arrays would start at index 1. And then in the late 60s, a small group of, turned out to be highly influential programmers decided to set the origin at 0, which is different than everybody else. All of humanity, since the beginning of counting, we have always called the first thing whatever number it is we have for 1, except for the programmers. We now count everything at 0. And that creates an instant off by one error when we interact with the rest of humanity. Because our idea of what is first is different than everybody else's idea of what is first, and so there's an opportunity there for things to go wrong. Even the mathematicians don't do this. So the mathematicians figured out that the origin of the Cartesian plane is at 0, 0, right? But when they count an ordered set, they still start at 1. Nobody knows how they do that. How can you know? They've got so I decided that we're right. 0 is actually the right answer. And I believe eventually we will teach the rest of humanity how to count. And we'll probably do that through STEM. It turns out the most important discipline in STEM doesn't get a letter. That's programming, right? All of the other letters, the most important thing they do is really the P's, right? And so I'm not saying that we should call it STEM, but I think eventually that way of teaching will filter into the rest of humanity and we'll all start numbering from 0. So in my book, I totally commit to that. So the first chapter is chapter 0. And the first page number is page 0. That's just because it's a book for programmers, right? It makes sense that it started 0. It wouldn't make sense to start with any other number. So while we're talking, so I decided the origin should be 0. And then I looked at 1. And it turns out 1 is misspelled, right? And you look at the rules of English pronunciation, there is no general rule or special rule which explains why 1 is spelled O-N-E, right? It just doesn't make sense. There's no reason for that. And it's just wrong. And worse than that, the first letter of the word for 1 looks like the symbol for 0. That's a bug, right? That is a bug. So I was at a conference in London a few months ago, and I was pointing this out. And I said, well, this is probably because of a problem with the Queen's English. So I said, Your Majesty, if you're watching, I'm going to assign this action item to you. You need to fix this. This is not a feature request. This is a bug fix. So, Your Highness, please get on it. So this is the chapter list. The chapter list is in JSON, of course, right? It's a JSON array full of objects that describe each chapter. Starting with chapter 0, read me first, because that's where we start, right? Read me first, I don't know if you remember, was a thing on the Macintosh. It used to be when you bought a new Macintosh and you opened the box, there'd be a whole bunch of paper in there. And one of them would say, read me first. And it was probably something about setting the thing up. Or don't forget to return your warranty card or something like that. And over time, various departments at Apple decided they wanted their stuff, like return policy stuff. Don't return it to the store, call us first and we'll figure out if we can fix it, that kind of stuff. So there'd be half a dozen things in the box that say, read me first. So this is where I describe what the book is about, what the conventions are, why we're spelling 1 differently, and all that stuff. So that's the introduction to the book. Chapter 1 is how names work. It turns out names are important because much of what we do as programmers is invent names for things. And so having a good strategy for how you do that is important. And it's also very desirable because we're so literate in the way we express this stuff. For example, mathematicians really like to use cryptic notation. 1 letter is enough to describe something. And we found in programming that doesn't work. Cryptic is not good for programs. We want to be explicit and literate. And so we want to be using full words and we want to use multiple words. But when we're using multiple words, the question is, how do we represent that? Because our languages don't allow it. There's one school that says we should use an underbar to represent what those spaces are. There's another school that says, no, we should be using camel case where we capitalize the words that are at the beginning of the word. And these 2 schools cannot agree because there's no good evidence to support either. And the reason for that is that they are both wrong. It turns out the correct answer is words with spaces. We should be able to write programs with words with spaces, right? That's how we write in English, and we're able to understand that. We have computers that can now do voice recognition. Why can't our programming languages do this? Why can't we see some set of words? And this dates back to the beginning of programming languages. The first languages in the 50s and 60s were on machines with extremely small memories. They were very constrained, and so we came up with a science of parsing, which mainly was optimizing memory. But that was when memory was counted in kilobytes, and we are now in gigabytes. I think it's time to rethink this stuff, that we can actually create more readable languages that look more like language. Chapter 2, how numbers work. So numbers are really important. Numbers are fundamentally all computers can do. Computers are just machines that transform numbers. And we've figured out ways of having those numbers map onto other things, so computers now mediate virtually everything that humans do. And JavaScript has numbers, and unfortunately, our numbers are based on the IEEE 754 floating point standard, which is a bad thing. So, for example, when your program is dealing with 0.1, that is not actually the value that's being represented. That is the number that's represented. And it's pretty close to 0.1, but it is not 0.1. And that's particularly a problem if you're dealing with money, right? Because when you're adding up money, you are legally required to get the right answer. And we don't. And so there are various strategies for how you cope with this. The best one is you multiply all of your dollars by 100 so that you're in cents. Cents can be integers. This system can handle integers correctly, so that's good. The problem is if your code has to interact with other code which didn't do that, you now have off by a factor of 100 errors, which if you're dealing with money could be disastrous. So we need to fix that. And so I show ways to fix that in JavaScript without requiring any changes to the language. In chapter 3, I develop a package of big integers. So we can have integers now that go to any length. They do not roll over like Java ints do. They don't get fuzzy like JavaScript ints do. They can be perfect and exact, as big as you'll ever want. Having that library, we then build a floating point library. Floating point requires that each number is represented by two numbers. One is the thing that is all of the digits, and the other is where to put the decimal point. And this library does that. So having this library, which lets you add, subtract, multiply, divide, and lots of other things, solves that problem. So we can now represent all of the numbers that JavaScript can and all of the numbers that are most important to humanity, which are the numbers that are represented by decimal digits. We can now do everything correctly. I think that's an important thing. Now, it turns out floating point is not complicated if you have a big implementation under it, because there's just not much complexity. Most of the complexity in floating point implementations are dealing with the limited number of bits and trying to keep as much precision as possible within that constrained set. I also, just for fun, give you a library for big rationals. So we take two big integers and express them as a ratio, one over the other. And so this will allow us to represent all of the rational numbers, which is an even bigger set of numbers. So there are other computations which people have said JavaScript cannot do, which it turns out JavaScript can do. You just have a little bit of JavaScript. In chapter 6, I talk about Booleans and the problems with bullishness. Everybody know about bullishness? So JavaScript has true and false Boolean values, which is great. But it also has the bullish type, which includes everything in JavaScript. And so all values are either truthy or falsy. And that was done intentionally in order to allow some of the idioms that were written in C to be written in JavaScript. And that turns out to be faulty and error prone. So I recommend avoiding bullishness as much as possible. You can't do it entirely because it's really deep in the language. But for most purposes, like in a condition of an if, you should really try to have a thing in there that's going to be a Boolean value and not necessarily a boolish value. I talked about how strings work, in particular how strings work in the face of Unicode, and how JavaScript was designed before Unicode was fully designed. So Unicode is a 21-bit character set, but JavaScript only has 16-bit characters, and the confusion that that causes and how to work with that, that's all explained. Chapter 8 is how objects work. Objects in JavaScript are not like objects in most other languages. They are more like hash tables in other languages, but they're fully integrated and built into the language. And they have this really lovely object literal notation, which is great. That's one of the best features in JavaScript. How arrays work. Arrays are one of the fundamental data structures in programming. You know, Fortran had arrays. That was the only data structure that it had. Arrays are extremely useful. Unfortunately, Fortran put us in a mode of thinking about arrays as things which are processed one element at a time. And so we set up a specific flavor of loop that does one thing at a time. And it turns out to be a really bad way of processing loops. So in ES5, we got some new array methods, which like for each and map, which are much better. I recommend using those only instead. Unfortunately, that set of methods is not complete. There's some things that you want that are not possible, like having loops or that processing go backwards, or being able to exit early out of that processing. So there's still stuff that needs to be done, but I recommend using those methods instead of having for loops. One potential benefit in the future is we could have a high level of parallelism built into JavaScript, so that if you used for each, or more likely map or reduce, and pass it an array of things, it would distribute the values in that arrays over all of the cores that are available and execute the function that you pass in parallel, which could speed certain kinds of programs up tremendously. So that would be a really nice thing. And you'll never get that speed up with for loops. How the bottom values work. So JavaScript has 2 or 3 bottom values. It has null, undefined, and nan. And in a well-designed language, I think you should have 1 bottom value, and we've got 3. So as much as possible, I want to simplify. The problem with null and undefined is you've got 2 values, neither of which is an object, which are very similar in some ways, but different in other ways. Whenever you have things which are very similar but different for no good reason, then you're going to have confusion. You're going to have people arguing about which one to use, or they'll try to use them interchangeably, but they're not interchangeable because they are different. So I recommend getting rid of one of them. And usually when given a choice of getting rid of something, I want to get rid of the one with the longer name, just because I don't want to have to type so much. And null has a well-understood meaning with computer scientists. We know that null is a thing which indicates the end of a recursive data structure. So it's better understood. And undefined doesn't make sense, right? Because what does undefined mean? It doesn't mean what mathematicians mean by undefined. And it doesn't even mean what programmers mean by undefined. For example, if you define a new variable and do not initialize it, JavaScript initializes it with undefined. So the variable you just defined has the value of undefined. That doesn't make sense. So given all of that, the one I decided to get rid of is null. And I'm using undefined. And the reason for that is undefined is the value that JavaScript uses. So if you have a parameter that has not been initialized, it'll be undefined. If you have a variable you didn't initialize, it's undefined. If you extract a value from an object or an array that it doesn't contain, you get undefined. In fact, JavaScript doesn't use null. So I'm getting rid of null. And by getting rid of that, I'm no longer plagued with the type of null equals object problem. So I recommend everybody do that. Chapter 11, how statements work. So there are 2 kinds of languages in the world. There are statement languages and expression languages. And the makers of expression languages have a lot of theory which explains that expression languages are superior to statement languages. Despite that, all of the popular mainstream languages are statement languages. But I think we have too many statements. So we can actually simplify. Some of the statements are problematic. We've already talked about the for statement. We can get rid of that. And so I give advice on the statements that we should be using and the statements that we really don't need. How functions work. So functions are the most important thing in JavaScript. Where we finally get it right. The type of functions that JavaScript has were inspired by the scheme language, which was the first language to really get this right. And so that's why JavaScript is an interesting language. It got lambdas before all of the other mainstream languages. JavaScript was first. It was followed by Python and Ruby, and eventually C#, and then even C++ and PHP do it in a half-assed way, and even Java does it now. So functions are great if we use them well. Chapter 13 is about generators. So ES5 added a feature called generator, which I think was a mistake. So the idea of a generator, which is a function, and each time you call it, you get the next value in a sequence, that's a really good, really powerful idea. But the way ES6 goes about it, I think, is completely wrong-headed. So this is an example of the kind of thing they want you to be writing. So this looks like a function that will yield a count each time you call it, where yield is a special kind of, is an operator rather than a statement, but it looks kind of like return, except it isn't. What it is, it's a function that returns an object that contains a next method, which when you call it returns an object that contains a value property which contains the next thing you're trying to get. So there's a lot of hidden complexity in that, and often hiding complexity is good, but in this case, the complexity is not well hidden, because where did next and value come from? You don't see those in that. In fact, the code that you write is nothing like what the code actually does. That one little asterisk up there completely changes what's going on. So this is what I recommend we do instead. We have a function that returns a function that returns a value. So we can call the outer function a factory, and we call the inner function a constructor. So we call the factory, it returns a constructor, and then each time we call the constructor, we get the next value. So you can see the correspondence between these two. This one, to my eye, is much simpler and also less error-prone and probably faster. So instead of having a function that looks like a function that returns a value, but is actually a function that returns an object that contains a next method that returns an object that contains a value, instead you have a function that returns a function that returns a value. So much simpler. This is good JavaScript. This is Python. What's it doing here? That doesn't make sense. Chapter 14, how exceptions work. So the idea of exceptions is really good. The idea is that we don't want to have every function call end up with something having to look at the result and ask, did something horrible and unexpected happen here? So that our programs can be written in a more optimistic way, that we assume everything's going to work most of the time. And in the weird cases where it doesn't, then we can have something that catches that and then can, try to reset the system or report problems or do other things. Unfortunately, because of errors in the design of the type systems in C++ and Java, exceptions have become another return path, become another communications channel. That those type systems do not allow a method to return all of the values which should be expected. For example, if you read a file, one of the possible return values should be file not found, right? That's not an exception. That's a normal occurrence. But the Java type system is so feeble that it does not allow that to be returned the same way that values are returned, so we use exceptions to do that instead. And so exception handling gets really, really complicated where the normal results are mixed up with the abnormal results. And the thing we really want the exception to do is to communicate something to the programmer when it really is one of these terrible errors. For example, we pass an immutable value to a function and it tries to mutate that and it fails, so that should throw an exception. Who should know about that? It's unlikely that the function that called it will know what to do, right? Our systems are not smart enough to do that kind of stuff. The person who needs to know that is the programmer, but that information is hidden in an exception object, which will get, dropped down the call stack and might get to a point where it's ignored or mutated or lost. So we've compounded two things. One is, how can the program recover if something goes wrong? And how can we communicate a failure? And we've made the two things one thing, and they really should be two separate things. So if a program realizes that it's in a state of error and it can't continue, then it should be able to write to some journal or communicate, maybe send an email or something to tell whoever needs to know that, the human who can fix it, who's smart enough to understand what the situation is and repair it. Telling the calling function is ridiculous, right? There's nothing the calling function can do about it, and there's a good chance the calling function will lose that information. It won't get communicated. So I think those two things should be separated. How programs work. So I talked about the history of programs going all the way back to the very first computer, where we would load a set of orders into memory and then execute them, and at the end, maybe some lights will light up and we'll get a result. That one of the early things that was recognized that was wrong with that was that we needed subroutines, and that sort of started us on this path toward modern programming language, which is great. One of the problems with the way JavaScript was first implemented in browsers was that programs were made up of separate compilation units, where each compilation unit is a script block or a tag, like a non-click tag or something. And so in order for that scheme to work, everything had to happen in a shared global context. And we learned in all of the other languages that global variables are evil. But we continued to do that for a long time in JavaScript until finally ES6 was modules. And there are some very good things about modules in ES6, which I talk about in this chapter. There are also very bad things about modules in ES6, which I don't talk about, because I'm a positive guy. And I'm always looking at, what's the good thing here? I don't like talking about the bad parts. I really don't. I'd much rather talk about the good parts. So, and there's a simple subset of modules in JavaScript which are great. I recommend that each module, first off, that you use modules because they're good, that you not use global variables anymore in any form, and that for modules that want to export something, they do one export. They'll export either a constructor function or an object, and in either case, that thing should be frozen so that we minimize the possible cross-contamination if multiple users of that thing. JavaScript allows modules to be written in much worse ways, where you can have lots and lots of exports and lots of imports from the same module, and all of those things create tight coupling, which is bad for modularity, so we really shouldn't be doing that. We should be doing the simplest form of import and export, and that's enough. We can write good programs with that. I talk about the this. So this was something that JavaScript does in order to support prototypal inheritance. And unfortunately, it comes with lots of problems. And I talk about those problems, and then I give the solution to the problem, which is to not use this, to instead do class-free object-oriented programming. that we can do programming in JavaScript without resorting to this. And I think this is JavaScript's gift to humanity, that this is a way of writing programs which avoids the tight coupling that we get in classical programming, that when you have an extends, that creates a tight coupling from one class to another. And that tight coupling causes problems. It creates bad modularity. It creates the possibility that a change in one class can cause other classes to fail. We can avoid that if we get rid of the classes. So this is the model that I recommend. It's actually an extension of the generator pattern that I showed you earlier. In this case, instead of having a function return a function, we've got a function that returns an object containing many functions, but all of those functions close over the same stuff that was in the constructor. And that's a pretty good pattern. So this is how I recommend we be writing our stuff from that now on. The downside of this is that it will use more memory. The good thing about this and prototypes is that allows us to take all of the methods that all of our instances are going to have and have just one set of them which are all shared through the prototype chain. And when JavaScript was invented in 1995, that might have been really important. But Moore's Law has continued to crank since then. And our memories are so vast, you've got gigabytes of RAM in your pocket. I mean, 20 years ago, we just couldn't imagine that. You know, Moore's Law doubles it every 2 years, and it's been, so it's just not worth worrying about anymore. I talked about how tail calls work. Tail calls were the most important feature that was added in ES6. And unfortunately, the least competent JavaScript engines have not implemented it yet, which really frustrates me because this is a really important feature. The idea is that if a function returns the result of calling a function, instead of doing a call return, it does a jump to the new function. And the effect of that is that we can have recursive functions which run as fast as loops. And it also creates new forms of programming like continuation passing style. With this feature, JavaScript finally becomes a real functional programming language, which is really important. And so if you know anybody at any of those incompetent companies, tell them to finish the tail calls. In fact, I think there should be a moratorium. No new features get added to JavaScript until ES6 gets finished. Because there's nothing in the new proposals that are as important and as good as that one. Purity is a really important idea that's becoming better understood. It comes from mathematical functions. In a mathematical function, you have a mapping of values, in and out. And it's a constant mapping. So it's not really about computation, it's really about mapping, about correspondence one to another. And so people have tried to adopt that rule and apply it to programming. So you have a function which its result is determined exclusively by its inputs, that it is not influenced by its environment, it's not influenced by anything else mutating in the system. Thing in, you'll always get the same thing out. And the good thing about that, there's a lot of good things about it. One is, once you've tested a function and you know that when that goes in, that goes out, you know that nothing else in the environment can ever cause that to change. So your programs become more reliable, because once you've shown this to be true, it will always be true. Another benefit is that we can run stuff in parallel. So we could, in a multi-core situation, we can run lots of stuff at the same time, and because there's no mutation going on, there are no read, modify, write races, and so everything stays fast. So we can get a performance increase, and everything stays good. It doesn't fall over like it does in Java. And the other benefit is that we get better modularity, because each function has extremely strong cohesion, because everything in that function is only concerned with producing a value. There's nothing else going on. Nothing is coupled to anything else. So we get really good modularity. We have a difficult time writing stuff with good modularity, but with purity, it comes for free. Unfortunately, purity doesn't work in the universe. Because in the universe, everything is changing. Purity works really well in a Turing machine or in the lambda calculus, but they don't interact with the universe. They don't interact with you. That humans are not pure. Every time you interact with a human, they might do something different. So I'm advocating a hybrid model. I think there is a lot of goodness that's in purity, and we should try to get as much of that goodness as we can because it's good and it's real. But at the edges, I think we still want to have impurity. I think the pure school is having difficulty in the part that interacts with the real world. They've come up with tricks like monads, which kind of make it look like they're solving the problem, but I don't think they're really there. So I advise being as pure as we can, but no purer. Eventual programming is what we've been doing in the browser since we started working in the browser, which will have a function that will pass to something, and it will return immediately, and the result will be communicated eventually somehow, usually through an event, calling an event handler. And that turns out to be a really powerful way of doing real-time programming. And a lot of what we do is real-time, and that's great. But it's hard to do, particularly in servers, because in browsers it's pretty easy because it's generally one click, respond to that, and then you're done. Whereas in servers, you get a message and go, well, I'm going to have to talk to that server, I'm going to have to talk to that server, and I may have to take the result I get from that server and send it to that server and so on. And so you get these really complex flows. And there are three popular mistakes for how you deal with that. The first one is called callback hell, where you have the next request is in the event handler of the previous one, and that gives you code which is extremely brittle, and it's hard to maintain, it's hard to deal with timeouts and other things. It's really an awful way to do it. The second mistake is called promises. Promises were invented at a company that I founded several years ago, and in their original form, promises were brilliant. They were a way of creating secure protocols between distributed machines, wonderful stuff. Fortunately, all of the new paradigm goodness was removed by the time they got to JavaScript. And so all that's left in them now is a really awkward way of doing control flows, which is not what they were designed to do, and that's why they don't do them very well. Then the other mistake is called async await. And this is something that came out of Microsoft, where you put these decorators on the code, and it allows for eventual code to look like sequential code. Because for people who don't understand how eventuality works, it's easier to pretend that everything is still sequential. Unfortunately, that's got two problems. One is there are people who really don't understand what their code is doing. It's very similar to generators in that way, in that you've got people who are writing code who fundamentally do not understand what that code is doing. That's always a really bad idea. But the other problem with it is they start putting the decorators everywhere because they really don't understand what it's doing, so all of the code becomes async, and that's not a good thing. So I think what we should do instead is embrace eventuality, because that is the next paradigm. We started doing that with JavaScript. Unfortunately, we got distracted in Node, but I think we can still get there. And in this chapter, I provide you with a library that I wrote called Parsec, which stands for parallel and sequential, which recommends that instead you write your code in terms of functions which each will do a unit of work. Like it'll call a database and get its result, or call some process and get a result. And then you take those calls, or those functions, and you put them into arrays, and then you give them to Parsec and say, I want all of these executed in parallel, and I want to get an array of all of their results when it's finished. Or I want this array processed as a sequence, which means as each one finishes, it sends its result to the next one, and Parsec manages all of that. And so we don't have the tight coupling of control flows and logic that we have in the three mistakes. It's modular programming. We've got the modules that do the work, and then we've got this framework which determines the flow between those modules. Much better way to write this kind of code. I talked about dates, going all the way back to Rome. I could go back further, but we're using the Roman calendar, so I go back to that. And some of the problems that occurred, anybody know what the word December actually means? It's the 10th month, yeah. So that's obviously a bug, right? So I talked about how that happened, and then I talked about how JavaScript copied the Java date class. The Java date class was not Y2K ready when it was released in 1995. I don't know if it's because they didn't see it coming or if they didn't think Java was going to last that long in the market. We'll never know why that happened, but unfortunately JavaScript copied it. And if you look at the date constructor in JavaScript, it is one of the best examples I've ever seen of the worst possible way of doing classical programming. Because it's a set of like 30 or so getters and setters. That's pretty much it. We should not be writing getters and setters. That's a really bad pattern. What we should be doing instead is writing high-level stuff where we're hiding all of the data, and it encapsulates something. So all of the methods are doing transactions, right? We want to have much fewer methods which are just focused on doing useful work. And JavaScript makes this easy because we can use object literals to describe all of the components of the transaction. So I suggest an alternate way of doing dates in which you have an object which you fill in with a year property and a month property and a day property and so on, and you pass that in, and it will turn it into other representations that you might need. I think that's an example of a modular way of writing a class. Who's heard of JSON? Anybody? Yeah. So in this chapter, I, for the first time in print, tell the story of the creation of JSON. That I got the idea for JSON working in Chip Morningstar's shed behind his house. We were having a startup in 2001, which was trying to do interactive applications in web browsers, which was a really radical idea at that time. And I talk about how we came up with the idea for JSON and how we named it and how it took off and why the JSON standard turned out the way it did. I look at what I got right and what I got wrong. Fortunately, I got enough right. And I also give advice to anybody who thinks that they want to design the next standard, things that I think would help them. Then I talk about testing. And the dilemma with testing, that testing cannot prove the absence of bugs, and that's really the thing we want to know. We tried other approaches. For example, we tried proofs of correctness. This was the most important outstanding problem in computer science, and it failed. And the reason it failed was it turned out that the proofs that a program is correct were much more complex than the program you were trying to prove. And it turns out complexity is the thing that makes it hard to know if the thing is correct or not. So that unfortunately failed. Then there were some people who had the idea of maybe type soundness will do that. That if we can prove things about the types of things, then maybe that will prove that the programs are correct. And unfortunately, that failed too. That types are beneficial, but unfortunately, we don't account for their value correctly. We give types credit for the bugs that they catch, which they deserve. We do not count against them the bugs that they fail to catch, and we do not count against them the bugs that they cause by forcing us to circumvent when they fail to allow us to do the things that we need to do. So when you look at types, if you don't count the negatives, if you only count the positives, they look great. But if you count everything, then I don't think they pay the freight yet. Maybe someday they will, but we're not there yet. So that means we still have to test, even though we know that testing doesn't work. And in order to help with that, I give you a new library called JSCheck, which supports testing over turns so that we can do eventual testing as well as sequential testing. And it also does random case development so that you can describe a set of generators which will produce types that go into or produce values that go into the testing system, and so it can generate hundreds or thousands of test cases for you. I talk about optimization and things that we do to make our programs go faster, and I give a lot of advice on how to do that well and how to do it badly. Well, no, I don't actually tell you how to do it badly, but I tell you that it is done badly, but I tell you how to do it better than that. Then I have a chapter about transpiling. It turns out that transpiling is an important application of JavaScript that we didn't know about even a few years ago. Now we now have lots of transpilers which are translating old languages into JavaScript. We've got transpilers that are generating dialects of JavaScript into JavaScript, and we've got entirely new languages which are being translated into JavaScript. And this is happening because JavaScript is a surprisingly good execution target because there's goodness in the language, that it comes with a really good memory system where all of the details of memory management are hidden. That's ideal for someone who's trying to create a language. And it runs everywhere, and nothing else runs everywhere. So JavaScript is where you want to go if you want to be everywhere. So I present a new language that I call Neo. And Neo is not the one, but it's an interesting language. So it is both visually different and semantically different from JavaScript, but also retains everything which is good about JavaScript. So this is an example of a Neo program. So this is the reduce function. It's similar to the array reduce function that we have in JavaScript. And I'll point out a few features of this program. The first is we have names with spaces. I expected applause at that point, but that's all right. So yeah, names with spaces. So, callback function, initial value, those are variable names or parameter names. We've got names with question marks. So any name is allowed to end with a question mark, and that's a very nice way of writing predicates. So, you can say if not an array, then or if it's not a function. Then the way we write functions is a little different. So when we were putting together ES6, there were a lot of complaints from people who said, we don't want to type function anymore, because you have to go, So we put in fat arrows, which I think was a mistake. Fat arrows are problematic. There are syntactic ambiguities that you can't return an object literal with them, that it looks like a block. And they're also easily confused with relational operators. So, and you don't know that thing's a function until you've read half of it already. You should get better warning. So instead, I've got a florin operator, and the florin operator takes the place of the function keyword. So it gets much smaller, and we don't need the parentheses around the parameters, so that gets smaller. So it's fewer keystrokes in most cases this way, but I think it's clearer that the thing is a function. So we considered stuff like this in ES6, and the prevailing opinion there was, if there isn't a picture of the character on a key that you can put your fat finger on, you are not smart enough to figure out how to get that into your program. And I said, that's not true. Those people are really smart. They'll figure out how to do that. Maybe their IDE will give them support, or keyboard macros or something. They'll figure it out. They'll get this in. So I'm taking that chance. I've got characters in this language which are not on the keyboard, but which I think make for better programs. The The assignment statement now requires a keyword at the beginning, and the keyword is let. And I got rid of all of the assignment operators because mutation is a problem. I don't want this language to be totally pure, but I want it to be much purer than the current language. JavaScript currently has 17 assignment operators, which is way, way too many. It's a celebration of mutation. But we want to be reducing the amount of mutation, and I want to make it clearer when mutation is going on. So in this language, let is the only place where you can mutate, where you can change the binding of a variable or change the contents of a record or an array. Let's see, then we've got new operators. Up there you see the V operator, which is made by a backslash and a slash together. This isn't widely known, but backslash was added to the ASCII set specifically to do this. The idea was that slash and backslash would fuse to create or and and. And so that finally gets into a programming language after, it's been 50 years or so since ASCII. And then greater than or equal, that's another of those characters which we should be able to use, right? So I got that in there. Yeah, so I don't know what's special about that one. So functions again, so we've got a nested function. And I still have a loop. So I took the 3 loop statements that we have in JavaScript and stripped them down to a single loop statement, which is just a simple infinite loop, and you need to explicitly break. Oh, and fail. So I got rid of exceptions, and we just have failures now. So this is the most radical thing I think I did in this language, and so I think this is the right way to go, but we'll find out. So that's my proposal for the next language. So there's no inheritance. It integrates objects and weak maps so that in this language, a record can have keys which are strings or arrays, which is something I wish that JavaScript could do, but it can't. Arrays act like arrays in that they actually have dimensions, and if you try to store beyond the current dimension, you'll get an out-of-bounds error. Numbers are big decimals, so we finally fix arithmetic. And so you can just 0.1 plus 0.2 will be 0.3 exactly. So at last, equal at last. And null, undefined, and nan are unified into a single value called null. And null also has a nice property that it will accept a path expression. So you could say null.a.b.c, and in JavaScript that throws an exception. If any place down that path, you get a non-object. But in this language, it's okay. If the path doesn't yield a value, you get null at the end, which is the right thing. So you don't have to go and between each piece. You just write the whole simple thing and it resolves. So Neo is not the one. It's not the next language, so it's missing a lot of stuff. It does not have regular expressions or any other kind of pattern matching. I think that the next language should have context-free pattern matching so that we can express a much larger set of languages. And it should also be non-cryptic. Regular expressions are so cryptic. If the thing is longer than an inch, you really can't be confident that you know what it's going to match. We can do much better than that. The character representation should be UTF-32 so that code points and code units are the same thing, so we don't have to have that distinction anymore. Everything is characters again, which would be good. We should have blobs in the language, so you've got a great big thing which is large and messy and totally encapsulated, so we can pass it around without having to understand what's in it. We should have a processing loop, an event loop, a message loop that should be built into the language. We should have process management. We've got processes in our environments, but in the next language, they should be first class. So starting a process, communicating with a process, killing processes, all of that stuff should be built into the language. We should have better support for secure networking because that's how the universe works now. And we should have support for parallel processing so that we can take an array of operations and spread them out and have them all operate in parallel really fast. Then in the next chapter, I talk about how to tokenize Neo, and then I show how to parse Neo, and then I show how to generate code in Neo, and then I give you a runtime that you can add to JavaScript, which allows JavaScript to run Neo programs. In chapter 30, I talk about WAT. Anybody know the WAT story? So there's a video on YouTube. Search for WAT JavaScript. And there's this lovely little video about a guy who opens up a console and starts typing in JavaScript expressions and getting big laughs. So for example, there's this one where array equals not array. You go, how could that be true? It turns out it is true. So in this chapter, I spoil all of those jokes. I explain why these things work the way they do. This is the only chapter that focuses on the really bad parts of JavaScript. And then in the final chapter, I describe how the book itself works. I show some of the software that I use to produce the book. And I give thanks to the people who did it. I talk about the fonts that I designed for the book. For example, I created a font called Programma, which is based on Microgramma, which I use for writing all the programs in the book, and Daily Bold, which I used for the subheadings. Some of you might recognize this. This is based on Chicago 12, which was the original system font on the Macintosh. So the very first mainstream user interfaces were expressed in this language, so it's in this typeface. So it's really an important cultural artifact for our profession. So I modernized it by getting rid of the jaggies, and I did that by making them straight lines, borrowing an idea from another typeface called Machine. So if you know anything about mid-20th century political corruption, the name of this font is really funny. It's on sale real soon. I wish it were on sale now, but it's not yet. But we'll get there. And it will be announced on howjavascriptworks.com. Yes?
Since your book is not published yet, I searched for the things to say, and I would call it something like a real other book more than myself. And because, I mean, quite frankly, I was at that stage when I was out of JavaScript started, and the only reason it has the first four letters in it is because it was marketed by somebody else in the job.
Right.
You know, it's technical. It's not,
Right.
so by you producing a book of JavaScript, you're furthering the parent. And I really would like to have the name of JavaScript because it's something new, so why don't you take the step to do it?
So he's complaining that the title of my book contains the word JavaScript, and he pointed out the obviously terrible problems in the name that were created by Netscape marketing, intentionally confusing, and that I'm propagating that confusion. Did I characterize that correctly? I'm having enough trouble just changing the spelling of one. No. So my goal is to get us to the next language. And I'm doing that subversively by talking about what's good about the language we've already got. And if I put a different language name in the title, no one will know what I'm talking about. Yes? Neo does not use semicolons. Yeah, so people hate the semicolons in JavaScript. I can understand that. But JavaScript does not work correctly all the time if you leave the semicolons out. So if you're writing in JavaScript, you've got to put the semicolons in. But I understand why people don't like that, and so I correct that in the next language. Yes?
I don't think that the idea of allowing spaces in names is a good one. Because when it's just one unit, it's very easy to see that this is a variable, where when you start creating it, you look at it, and I think it would be a very distracting.
Yeah, he thinks that names with spaces are going to be distracting, and that's because he's an old guy. But I think when you actually try it, it will actually be very good. One more.
Is let the meal discouraging formal installation?
I'm sorry?
Is let in meal discouraging formal installation variable?
Yes, it is. Okay, I'm sorry that the book is late. My original plan was it was going to take a month to write and ended up taking a year. And that's because it is a software project, and I found that the making of good software takes time. If you try to make it take less time, it takes more time. Thank you.
Sitting by your side, sunlight gliding in the night, watching how the tide comes in. Dreaming of a boat setting sail all alone, heading for a paradise. Found my better me in the small things you see. Remember when they seem so close. Promise to hold on if the waves getting strong, but we change our course with the wind. Found my better me in the small things you see, discovering our home again. When the day fades away and there's nothing left to say, I'll read your thoughts out loud. In the golden hour, we're breaking like waves in the sea. In all the lies that drown in golden hours, and all our dreams feel so real. Good time, come over here. Good time, come over here. In the golden hour, we're breaking like waves in the sea. In all the lies that drown in golden hours, and all our dreams feel so real. Good time, come over here. Good time, come over here.